Okay, in this section, we're going to be talking about inductive reasonings and conjectures. And inductive reasoning is just one type of reasoning that we're going to be discussing. And now, inductive reasoning is a reasoning that you've all used nearly every day. Inductive reasoning, by definition, making a conclusion based on observations or patterns. And let me give you an example of you using inductive reasoning. Let's say that John every Thursday wears his red shirt. No Thursday has ever passed that he has not wore his red shirt. So, man, tomorrow's Thursday. I bet John wears his red shirt. That's an example of inductive reasoning. Now, inductive reasoning is not always the best reasoning. It's not always the best method of coming up with what's actually going to happen in real life. Inductive reasoning sometimes can be wrong. Well, John's mom forgot to wear or wash his red shirt last night, and it's even though it's Thursday, he's not going to wear it today. So, inductive reasoning, even though we use it a lot, it might not always be the best method. Now, conjecture is a concluding statement reached using inductive reasoning. Now, I just made a conjecture. Since John always wears his red shirt on Thursday, I bet, and anytime you start that I bet, that's your conjecture. I bet he's going to wear his red shirt this coming Thursday. That is your conjecture. That's what you think that is going to happen. It's a concluding statement. That's the conclusion that I come to. Okay. These next few examples are actually going to ask us to use our inductive reasoning. Now let's do it. Find the next 5 terms in the sequences and then write the conjecture. Okay, the next 5 terms of this sequence, let's see, 38, 31, 24, 17. We're going down 7 each time. So again, inductive reasoning based on patterns. We're looking for the pattern here. So go down 10, go down 10 more, go down 10 more, go down 10 more, or excuse me, 7. Go down 7, down 7, down 7, and down 7 more. And that's going to be the next 5 terms. So the conjecture to find the next term, you will subtract, you'll subtract 7. So that's what we're doing each time. So my conjecture is my guess as to what's going to happen. So instead of on the next ones, I'm going to write an abbreviated version of that. So 2 to 5, that's adding 3, but then we go to 11, which I added 6. So I added 3. Let's try to figure out our pattern here. I added 3, then I added 6, then I added 12. Wait a minute, I see I'm doubling that each time. So next time I'll add double that, which is 24, so that'll give me 47. Next I'll double that and I'll add 48, which will give me 47 and 48 is 95. Then I'll add 96, which will be 191. Now here's another pattern too. I noticed that I'm always adding one more than that. From 5, add 6 to it, 11, add 12, 23, add 24, 47, add 48. So either conjecture you can use. So I'm going to add 192 next. That'd be 383. Then I'm going to add 384, which would be 767. So to find the next term, let's see, we can put that we will double the amount you add or added to the previous term. Just something to tell what did you do to find that next term, okay? 1, 4, 9, 16. Now this is a sequence that gives a lot of people fits, but once you see it, it's hard not to see it the next time. 1, oh, that's 1 times 1. 4 is 2 times 2. Or, yeah, 2 times 2. 9 is 3 times 3. 16 is 4 times 4. These are all your perfect squares. So 5 times 5, 6 times 6 would be 36. 7 times 7, 49. 8 times 8, 64. 9 times 9 is 81. So the conjecture is to find the next term, maybe square the, let's see, to find the, here, let's write it like this. To make it more mathematical, to find the nth term. Now, what do I mean by the nth term? Like to find the 7th term or the 8th term or the 9th term. You will do n to the 2nd power. So how do you find the 10th term? You do 10 to the 2nd power. How do you find the 9th term, which we found here? You did 9 to the 2nd power. So that's one way of writing that. A, D, G, J. Let's think about that for a second. If we look at the alphabet, we have A, B, C, D, E, F, G, H, I, J. And we have A, D, G, J. Notice what we're doing. We're skipping 2 letters is all. So J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y would be the next letters. So I'm just going to put, instead of writing all that again, we're just going to do skip 2 letters would be our conjecture to find those other terms. The next one, 7:30 to 7:55. Well, I know that's 25 minutes later, but let's check this, 8:20. If you do 20, and that is correct. So we're just doing 25 minutes later. So that'd be 8:45. 15 would be 9, so that'd be 9:10. 25 minutes later is 9:35. That'd be 9:50. No, it wouldn't. It'd be 10 o'clock. And then 10:25. So all I'm going to put is 25 minutes later instead of writing out a big long explanation. Oh, I like this one. 3, 1, 4, 1, 5. 9, 2, 6, 5, 3. And I'll let you think on that for a second. Here, see if this helps. 3.1415 dot dot dot. These are the digits of pi. Now, I don't expect you to have memorized or knew that, but that's just showing you that the whole purpose of all this was just to explain to you that these are conjectures. A conjecture is an educated guess as to what's going to be next. Okay, that's the whole purpose of this lesson, is make sure that you know inductive reasoning is based on, we're looking for some sort of pattern. And we use inductive reasoning in our daily lives when we base our conjectures on patterns as to what has happened before. Now let's explain a counterexample. What we mean by a counterexample. A counterexample, by definition, is an example that shows that a conjecture, which is our guess as to what's going to happen, an example that shows that a conjecture is false. Not all conjectures have to be true. Okay, those conjectures that we made on that previous few problems, well, some of those might have been false. That might not be the next term in the sequence or whatever. So examples. Determine whether the conjecture is true or whether it's false. Now, if it is false, they want you to provide that counterexample telling them why you think that this is false. Okay, let's try these. The sum of any 2 consecutive integers is always odd. Now, consecutive integers, that's like 3 and 4, 7 and 8, 9 and 10, 19 and 20. Now, will those always be odd? I don't know. Let's see. 3 and 4 is 7. 7 and 8 is 15. 9 and 10 is 19. 19 and 20 is 39. What about some negative numbers? Negative 3 and negative 2 actually would come after. That'd be negative 5. 0 and 1. Negative 1 and 0. Looks to be always odd. I'd say that this is a true statement, a true conjecture. Number 2, the product of two numbers is always larger than either number. The product of two numbers is always larger than either number. So 2 and 3, if you multiply them, product, you get a value that's bigger. But is that always going to happen? Will you always, when you multiply two numbers, will you always get a number that is bigger than either one of those numbers? Now, 15 is bigger than 3 and 5, but will that always be the case? What about negatives? Negative 3 times negative 4. Now that's a positive 12. That's bigger than, let's see, always bigger, always larger than either number, always larger than both of the numbers. Now there's a few ways that I can disprove this. One way is, what about if you did like negative 3 times 10? That's negative 30. Negative 30 is much smaller than negative 3 and 10 both. Okay, so that's one counterexample. There's your counterexample. Here's your another counterexample. What if you did 1/2 times 6? You get 3. Now, is that bigger than either number? That's bigger than 1/2, but not bigger than 6. So a couple of counterexamples there. So this is a false statement. That is not always true. If you can come up with a single counterexample, then that's not going to be a true statement. Okay, number 3, the product of two perfect squares. Now, perfect square is numbers like 4 and 25. 36 is a perfect square. 9 is a perfect square. So the product of two perfect squares is always a perfect square. That's interesting. 4 and 25 is 100. That's 10 times 10. That's a perfect square. 36 times 9, that is, let's see, 30 times 9 is 270 and 54, 324. Now, if you want to see if that's a perfect square, try to come up with something that multiplies to give you 324. And oddly enough, that would be, let's see, 3 times 6, 18 times 18. So it's 324, so that does work out. But does that always work out? And again, all you would have to do is find a single counterexample to where it doesn't work. However, this actually does. No matter what perfect squares you try to multiply, you'll always come up with another perfect square, which it actually leads us to simplifying radicals and other things that we did in algebra. So that is true. If the area of a rectangle is 6, the dimension must be 2 by 3. So if you have a rectangle that has an area of 6, then it has to be a 2 by 3 rectangle. Well, yeah, that has an area of 6, but what about a 1 by 6? To find the area of a rectangle, you do length times width. 1 times 6 is also has an area of 6, so that right there would be your counter example. So that would be a false statement. Dividing by 2 always produces a number less than the original. Like 10 divided by 2, that's smaller than 10. 6 divided by 2, that's smaller than 6. What about if you divide a negative by 2? Negative 8 divided by 2 is negative 4. If you think about your number line, where is negative 4, negative 8? Here's 0, negative 4, negative 8. Negative 4 is larger. So when you divided negative 8 by 2, it gave you a larger number. There's a counterexample. This would be a false statement. Vertical angles are never complementary angles. We talked about vertical angles last chapter, and let's remind you what vertical angles are. When you have two intersecting lines, these two angles are vertical. Okay, they're never complementary. Well, we knew that from last chapter, vertical angles are the same. So if that's 30, then that's 30. That would make this 150 and this 150. They're also vertical. They're the same. But could they ever be complementary? Well, complementary are two angles that add up to 90. So vertical angles are never complementary. Let's see if we can come up with some vertical angles that add up to 90. Well, they have to be the same. They have to add up to 90. So two angles that are the same that add up to 90, what if they're both 45? which would make these 135 and 135. These are complementary and they're vertical. So that would be my counterexample. So this would be a false statement. Number 7, if A times B is 0, which means if you multiply one number times another number and you get 0, then either A is equal to 0 or B is equal to 0. One of them has to be 0. We'll try to come up with something. What if A is 7? And 7 times B is equal to 0. Well, that would mean that B would have to be 0. What if B is 6? Then that means A is 0. What if A is 3? Then B is 0. So if A times B is 0, I would say that in order to multiply two numbers to give you 0, yeah, one of them's got to be 0. And you'll learn in algebra, if you don't remember, that that's actually called the zero product property, and that would always be true. One of them's got to be 0 from the zero product property. Two angles are supplementary. Okay, stop for a second. 180 degrees. They add up to 180. Two angles add up to 180, or two angles supplementary to the same angle must be congruent. Okay, two angles that are supplementary to the same angle. Let's say that you've got a 50-degree angle. And you've got two different angles that are supplementary to this one. Well, if they're supplementary to 50, this angle is supplementary to it, it has to be 130. If this angle is supplementary to 50, it has to be 130, so they're the same. What if you had a different size angle? What if you had an 80-degree angle? You've got two angles that are both supplementary to the 80. Well, this one's 100 because it's supplementary to 80. This one's 100 because it's supplementary to 80. Well, yeah, they're the same. So two angles supplementary to the same angle have to be congruent. I would say that's true. And that's actually, we'll learn later on, is a theorem. All states' names have at least two syllables. Not true. Okay, there's your counterexample. That would be a false statement. Squaring a number and adding one will always produce an even number. Now, that's a good one. Squaring a number. So let's start with 3. Square a number and add 1 will always produce an even number. Squaring a number and adding 1 will always produce an even number. That's odd, so that would be a false statement. And again, the terminology that you need to learn from this is your counterexample. Number 11 and 12, you're asked to write your own conjectures. And so these are entirely, they can be different for each person. Write your own conjecture, then trade with your partner and determine if the conjecture is true or false. And we'll write one ourselves and just see if we can come up with if it's a true or false conjecture. And here's your one. The product of two odd numbers will always be odd. So a conjecture could be anything that, hey, I think that's true. So that would be left up to other people to find out, well, is there any reason that that would not be true? Let's look at some examples of this. 7 and 5. 3 and 9. 1 and 5. 3 and 11. The product is always odd. 5 times 13. And you'll find out that that's actually a true conjecture. So again, conjectures can be true or false. The way that we figure out if they're true or false is we're going to use some inductive reasoning. And if we come up with one example to make it false, then it's going to be false because of that counterexample.